was the last one on R, and then 13 we switched chapters. So if we got through 2 chapters today, that would be big, right? So let's see what we do. Okay, number 10. Notice these are fifth roots. So we've got the little index shown, and inside the index is fifth root. We cannot subtract or add radicals unless they're exactly the same roots, exactly the same everything about them, and then they can be combined. So I'm thinking maybe there's some way that this one reduces down so it'll look like this one, and then we'll be able to combine. Okay, notice this radical does not reduce. There's not enough stuff in it. Like this m to the first, because you're doing a fifth root, it would need to be at least 5 to reduce. So it's too small for anything to come out of that. P squared, same thing. It needs to be at least 5 if you're going to take fifth root to get something to reduce out of it. So that's not reducing. So that term's kind of sitting there. But the term in front of it has enough to reduce. Are you seeing m to the 11th is big? Much bigger than the fifth root, so it's going to reduce. So like John said, we could do the division thing. We could say 11 divided by 5. How many of those m's are you going to be able to bring out of that root? 2 sets, right? So you'll be able to bring out m squared, and you're going to have how much left over? And you're going to have an m left over. So you can demonstrate it by saying m, 11 times and circling the 5 sets. I wanted you to see that, but division is faster. 11 divided by 5 brings out 2 of those, with 1 left in. Let me go ahead and show that 1 left in. So how many p's will you bring out of the radicals?
1.
Just 1, right. Your 7 divided by 5 brings out 1 of the p's, and how much is left over?
P squared.
P squared. Great, great. Now notice, it must have been set up like this, right? It works out so that you have like terms. If you have exactly the same radicals, you're allowed to combine the coefficients. These combine. And notice these are like terms to combine. 9 m squared p and minus 7 m squared p would combine to be 2 m squared p of that common radical. So that's the final step on that one. Oh, I was trying to pause, but I'm not patient enough. This is a good spot for us, right? Are you okay? Can you copy it?
Yeah, I got it from her.
Okay, great.
I almost have it.
All right, number 11. Normally, I reduce every radical first and then proceed from that. But in this particular problem, you're better off if you multiply first. In the numerator, it works out well. If you multiply this together, it cancels well with the denominator. So that's the strategy I'm going to use. You are allowed to multiply radicals if you have like indexes. Since those are both cube roots, you're allowed to say what's in here times what's in there. So 27 times 3 is 81. X is only x. Y squared times y squared makes y to the 4th, and it's still a cube root. Don't forget your root. It is over this denominator. And then, just like you're allowed to multiply if they're both cube roots, you're allowed to divide if they're both cube roots. So, as long as there's no loose plus or minus signs, you're allowed to reduce. That's the big rule. Make sure of that. Earlier in chapter R, we had a lot of loose plus and minus signs, and we had to factor first. So anyway, that's what I'm saying. You're allowed to cancel this. Everything is just multiplied together there. They're both cube roots. It's all fair game to reduce. So the x's cancel, the y4's cancel, and 8 and 243 reduces to a 1/3. So the whole numerator cancels out to be just a 1 over a cube root of 3. So it reduces down, almost disappears, right? But you still have that 3 in the denominator. Rule with radicals is you're not allowed to leave a radical in the denominator, though. So we do have to clean this up. So we have to times it by something that makes it perfect, that brings it out of the radical. Now remember, if it's a cube root, there needs to be 3 of those to bring out 1. So we can't just times it by another 3. It's not enough. We need to times it by 2 more 3s. Or if you want to just say we're timesing it by 9. If you multiply that by 9, it's the cube root of 27, which is perfect. Do the same thing to top and bottom, right? Whatever you do to the bottom, do to the top, keeping the balance on our fractions always. So cube root of 3 times cube root of 9 is cube root of 27. And on the top, 1 times cube root of 9 is cube root of 9. So then that is going to stay like that. Cube root of 9 over cube root of 27 is 3. And that is preferred form over this because there's not a radical around the denominator. Did we make it? Okay, cube root of 9, notice, does not reduce. There's not enough in it. There's nothing perfect inside of it. It's too small. It's 3 to the 2nd, and it's a cube root, so it's not enough to reduce. All right, last radical problem, number 12. Same rule about not having a radical in the denominator applies here. You cannot have a radical period in your denominator. If it is just a one-termer, you can times it by something to fix that, just a one term as well. But if it's a binomial, the only way to clean up a binomial, to get rid of the radical, is to times it by its conjugate. Conjugate means the different sign, change its sign. So let's make this 7 square root of 2 plus square root of 7. That's considered the conjugate. Whatever you do to the denominator, you do the exact same thing to the numerator. Okay, in the numerator, this needs to be distributed. Since it's just one term, it multiplies into this binomial. It makes 7. Now notice there's a 7 that's not under a radical. It's staying on the outside. It's like 7 times a 1 understood here. So there's 7 in the front, out of the radical. Square root of 7 times square root of 2 will make square root of 14. Then square root of 7 times square root of 7 would be square root of 49, or just 7. It's kind of that it would bring one out of the radical. You'd have a pair. Square root of 7 times square root of 7. Since there's 2 7s, you can bring the 7 out. So it does not have a radical around it. In the denominator, this is the FOIL method. So first would be 49, because there's the 7's on the outside, and then it's the buddy thing, right? You've got 2 and 2. There's a set, and we're doing square roots. So 2 brings out 1. So it's 49 out, and then you're bringing another 2 out. So it's really going to be 98. The first times first gives you a total of 98. The outer, we have a 7 on the outside, and then a square root of 2 and a square root of 7, which makes square root of 14, which does not reduce. The inner times the inner will have a negative 7 and a square root of 14. Now listen, you kind of should just anticipate that. If you're times by the conjugate, that always happens. The inner and outer should be opposites of each other. So once you do this quite a few times, you just know that's going to cancel out. And that's a good thing, because we're trying to make it not have a radical. Continuing though, the last times the last, we have the buddy thing. The 7 and the 7, both under the radical, brings out a 7. The signs are different, so it's minus 7. And so again, our goal, times by the conjugate, should always happen that the radicals disappear and you have nice rational numbers, 98 minus 7, which is 91. And then our last step is always think about if this thing will reduce. If there's any way you can factor out something, a common something that reduces from all of our terms. We can factor out a 7 out of the numerator. It leaves square root of 14 plus 1. And then you're allowed to take the 7 and 91 and reduce that out. I think it's 13. Yeah, I think 13 times 7 into 7 and 7 into 91 reduces to a 13. So we have square root of 14 plus 1 over 13. Now, some of you all memorized to do this by just saying if all three terms have a common factor, you can reduce by that. So you see the 7s there. 7 into 7 is 1. 7 into that cancels that out, leaves that. And 7 into 91 is 13. That's fine too.
How do we get from 7 square root of 14 plus 7 to the just plus 1?
I factored the common 7 out, like a GCF. I brought that out of the two terms. And then I said 7 times square root of 14 is that. And 7 times 1 is that. So I sort of undistributed the 7, factored it out. I think, though, what we've mainly focused on when we've done these, we just say if there's a common factor in these three parts, you can reduce. Because we do that with the quadratic formula as well. We do that a lot with that last step of the quadratic formula. If the 3 places left in the formula reduces, you can reduce by that factor. Okay, so that's chapter R. I'm going to try to do just a little